Okay, just recapping what we talked about. We're dealing with algebraic fractions, but you might remember that, I gave you the initial example of saying what we're doing today is not really adding two fractions together. It's like going from one fraction and trying to break it into a sum of two. And we talked about how with partial fraction decomposition, that denominator here could be thought of as 2 times 3. The 6 is 2 times 3. And we said we could look at some number over 2 and some number over 3. And, so it's like a starting right here, not knowing what two separate fractions we have. And we came up with a method to find A and B in example 1. Actually, we're doing that in AMA. Here's my question to you, though. This might get a little bit more interesting. What if I gave you something like 3 over 8 instead of 5, 6? You see, the 8, if you were to just do some prime factorization, and think about it, the prime factorization of 6 would be 2 times 3. Why am I bringing that up? Well, that's what we talked about right here, 5 over 6. What's the prime factorization of 8? 2 to the third, isn't it? 2 times 2 times 2. And kids would say, well, yeah, of course. What does that have to do with it? Well, wait a minute. That means that maybe my fractions that would add up to 3/8, maybe they just have a 2. That's 2 to the first. Maybe they have 2 to the second. Maybe they have 2 to the third. Do you see what's happening? When your denominator has a factor raised up to a power other than 1, just like you'd see right here, 3/8, I'm making a bold statement right here. I'm saying, actually, maybe we could find 3 fractions that could add together. Why? Because each of those factors, every power of that prime, could come into play as a possible fraction. Guys, that's what this box right here is really saying. Because otherwise, if we don't talk about that, that looks very confusing, doesn't it? You'd say down below we might have something like ax plus b to the n. They're saying, oh, you've got ax plus b to the 1, ax plus b to the 2, ax plus b to the third, all the way up to n. That's just doing this little work off to the side here. So when you see a factor raised up to something other than 1, you have to represent all powers up to that final exponent. Yes?
Does it matter if we use a sub 1 and a sub 2 or a
I'd actually prefer to just use A, B, and C. I know our author looks like he's using A sub 1. Honestly, it doesn't matter. I just find that it's easier to write separate letters and then things come together a little nicer, right? Okay, well, with this in mind, let's take a look at example 2. And guys, I'll tell you what, the very first thing I want us to do is to take this function right here, the 2x squared minus 12x plus 4. And by the way, let's even begin to start factoring down below. If I gave you x cubed minus 4x squared, what could get factored out? What could you pull out from both of those? X squared, and then what would be left? X minus 4. You always look for your greatest common factor first. You always ask, what's the largest factor that I could pull out from both? And that would be x squared here. So what am I getting at? This is exactly what we were just talking about a moment ago. You'd say nuts. Down below, I have a factor that isn't raised to the 1 power. Thank goodness it's not as tough as that last example where we had a denominator of 8, and that's 2 to the first, 2 to the second, 2 to the third. But my goodness, what on earth does this really mean? It means I could have a over x to the 1 plus b all over x to the 2. every power starting at 1, increasing up to this final power of 2, has to be represented. If I would have had x to the 4th, I'd have to have a denominator with x to the 1st, x to the 2nd, x to the 3rd, and then x to the 4th. Okay? But are we done right now? Is this as far as we go? No. What else do I need? A c over x minus 4. So this is just getting us started. We can say, well, that's really just our basic setup. We're going to be able to have all powers of x up to x squared, and then we're just going to have our singular x minus 4. Now, I don't need to tell you this is a tougher problem, right? So here's the thing. We could multiply through by our LCD. So we're going to multiply by x squared x minus 4. This, like I said, guys, is not a step that we generally even wind up showing work on. The left side, I hope you will agree, just works out to 2x squared minus 12x plus 4. I guess what I'm really getting at is when you multiply a over x times this, remember each individual term is being multiplied there, what would cancel out? Just one of the x's, God bless you. And all of a sudden we get this scare where we go, oh my gosh, look at that. After the a, we don't just have one factor multiplied to the a. We've got a couple of things, don't we? We've got an x and an x minus 4. And then you'd say, well, what about the b here? If we had the b over x squared times x squared minus 4, what's left? Well, thank goodness, this is much nicer, isn't it? That's just b times x minus 4. And then what? Finally, you could take your c over x minus 4, and if you're multiplying here, what's left, guys? X squared times c, or c times x squared. Now, to be sure, I don't want anybody to think that you can't do this. You definitely could do what we were doing before and make some clever substitutions for x to help us out. What's one obvious x value that would be nice to get plugged in? A 4, you bet. What's another one? 0. And you may do that for sure. But that being said, sometimes kids will very quickly say, now wait a minute, that's not going to be enough. I'm looking for 3 unknowns. Do you see what I'm getting at? So you might wind up with a system of equations when you do that. Sometimes you find one variable very quickly, and that's all well and good. That's fine, you can do that. What I'd like to do instead is show you a new method where if you learn this, you're going to be so thankful that you did. It's going to open up a new way of thinking mathematically for you. It's going to look worse, though, at first. Okay? Here's what I'm getting at. I'm going to FOIL everything out. Sometimes kids are like, oh my gosh, you got to be kidding me. Nope. ax squared minus 4ax. Here I'm going to get bx minus 4b plus cx squared. And then kids will say, oh, that's nice. Okay, let's stop right there. Well, oh, no, not quite. Tell you what, I want to combine my like terms. Kids will say, Mr. Dobner, you can't. ax squared and a cx squared, I don't know what a or c are. But imagine that you only had ax squared and b and cx squared there, only what's highlighted in yellow. That's the only thing I gave you. Couldn't you factor out an x squared from it? And if you did, you'd be left with a plus c. Redistribute x squared in here if you'd like, and you'll see that's exactly what's happening. Think of it this way. If a would have been 7 and c would have been 2, you'd say take 7 plus 2, and then it's that x squared. Right? That's what you're really doing, adding like terms. You know, it's funny. My older son, he's doing some basic algebra right now, and I was just helping him last night, and we were talking about adding like terms. I said, just add those numbers in front. Right? Even if it's an A and a C, you'd say, I don't know what it is. Well, that's okay. It's still A plus C. And then you'd say, no, wait a minute. What about your X terms? You'd say, no, wait a minute. There are only 2 of those. Yeah, but I could pull out an X. And if you're really, really clever, I kind of like to do this, but you don't have to. You could write negative 4A plus B, or you could change the order. Right? Now you'd say, well, what else do we have? Well, now we have just this minus 4B. And guys, right now, undoubtedly, I think you're probably looking at this thinking, and this was going to help somehow? I'd like to introduce a new way for you to think about problems. You're saying this quadratic on the left is equal to the other quadratic on the right. This is called coefficient analysis. The quadratic on the left is equal to the quadratic on the right. Kids will say so. So that means 2's in front of x squared. So is a plus c. That means a plus c is equal to 2. Didn't want to do that. Behave. There you go. So you've got a plus c is equal to 2. Oh, how about that? And then you come over here and you'd say, well, what's in front of x? Negative 12. Okay, so what's negative 12 going to equal? Well, what's in front of x over here? If these two quadratics are equal, and that's what we're saying, the only way they're going to be equal is if the number in front of x over there is equal to negative 12. Oh, how about that? Finally, you could say, well, let's see, we also have our constant right here. Oh, look at that. The constant 4, tell you what, maybe even want to make a little bar here to separate that. You'd say 4 is going to equal negative 4b. Guys, right now we're in a much better way. Go to that last far column. Guess what b is? Divide both sides by negative 4. You got b is equal to negative 1. And you'd say, well, what now? Well, go to the middle. Now that you know b is equal to negative 1. Now, this isn't the nicest looking equation, but it's okay. Negative 12 equals negative 1 minus 4a. I can add a 1 to both sides. I'll get negative 11 is equal to negative 4a. Don't panic if you get a fraction like this. You will get fractions like that in this section. Don't panic. I should have said that even with example 1. Don't let that scare you or worry you. And then what? You could say, well, now I'm going to plug that over here and get 11 over 4 plus c is equal to 2. Now, 2 is really 8/4. And if I minus 11/4, I should get negative 3/4. Right? So you can think, well, did this help? Yeah, what a tough problem this is. It's definitely one of the most tough that you can see right now. But this integrand can now be decomposed, and it can be separated into those 3 fractions. Let's see what our new integral will look like. This new integral, let's see, we said it was a over x. It was a over x to get you started. That's 11/4 all over x. Now we'd say we've got b over x squared. That's that. And then what? We also had a c all over x minus 4. Well, our c is kind of this little ugly thing right here. But guys, your new integral, it doesn't have the prettiest fractions in it. But that is something that you can break down. Okay, is that making sense, I hope? Okay, so tell you what. We're going to finish this up. What's the antiderivative of just this over x? We get what? 11 over 4 ln of the absolute value of x. This right here, do a power rule. x to the negative 2, you bump it up to the negative 1 power. You divide by negative 1.